Okay, the last section of today's lab is going to apply clustering and principal components analysis, PCA methods to one of the data sets in the ISLP package. So this is a microarray data set, and it has the feature that it's going to be more data than we saw in our earlier examples. We only looked at toy data sets and with 4 features for the USA arrests, and we generated data for clusters as well. Okay, so this data is quite a wide matrix. There's 64 cases, and roughly 7,000 features. And
the cases are different types of cancer.
Yeah, these are different tumors, and we have some biological measurement, microarray measurement on each of the 7,000 different measurements on each tumor. So in clustering here, we're looking to see whether, in terms of these microarray measurements, whether different tumors are related. So we might expect, if we knew that what kind of cancer they were, which we do here, we have labels for each of them, we might expect that, breast cancer tumor behave similarly within themselves, and leukemia behave similarly within themselves. And we're going to try and see whether that happens. So often when doing clustering or PCA, we might have some label that's held out that we don't use to fit these unsupervised methods, but we can, as at least a visual validation, we often will color points in a principal components analysis by the label to see whether this PCA analysis reconstructs somehow these labels. And if you look around online, there's actually a really nice, what is it? Is it November? Is that the genetics article? There's a really nice coloring of a principal component analysis of genetic data in Europe that reproduces the map of Europe.
Oh.
That's an example of one of these things. Novembri, I think, is the author. Yes. Okay, moving on. So we have 64 rows and 7,000 features. Now, if we run PCA, in the USA arrest data, we had 4 features and we got 4 principal components. So, we might hope that we get 7,000 principal components, but of course that's not going to be possible, right? So PCA is only going to give us, the minimum of, I think, the number of observations minus 1 and the number of columns of the data. So we're going to get 63 principal components.
At most.
Yes, yeah. We won't have to keep all of them, yes. Yes, of course, it could be less. The mathematician speaks. Okay, so here we have a summary of the different, the labels. So we can see there are, I think, 13 different kinds of cancer tumors, and they're broken down. Some of them have names that are interpretable to many of us, and these are very sort of specific ones. Okay, so let's run PCA on the microarray data. We're going to scale the data, though in this case, since all of the measurements are in the same units, they're all the same kind of assay, we may not need to scale it, but just it's common practice to scale it, so we're gonna continue with that. Okay, so let's see. We can find the principal component scores using the fit transform method, and we're going to again make a scatter plot. And as I said before, it's common practice if you have a label to label the plots in a this is something like the biplot we saw before, though I haven't added the vectors here for the directions. And in fact, that would be pretty dense, right? There would be 7,000 vectors or so. Mm-hmm. This is again the piece. This is the first and the second, and this is the first and the third. And what we're looking at here is try to get a sense of whether there is clustering in these principal components. And there's, these green ones are in similar location for the first 2. There's some evidence of clustering. Again, the color map is not. It may be not optimal because I can't actually tell whether this blue is different from that blue just by looking at this.
Yeah.
So probably best to make a better color map if you can. So there is an argument to the scatter plot that would allow us to change the color map. Okay, so let's take a look at the the sort of similar plot we saw for the USARS data, we're going to plot the percent variance explained and the cumulative percent variance explained. So remember, for the USARS data, I think the first one, the first principal component had 60% of the variance explained.
Right.
So here, well, 15%. And that's actually still quite a lot for 7,000 variables, right? If it was sort of completely randomly spread, it would be 1 out of 7,000 or so. So now, inevitably, if you're going to use these principal components for more than just looking at plots like this, you might use, for instance, you might use principal components in regression, like we saw in the end of the lab in chapter 6, though we didn't cover it in the video. It's contained in the textbook. You'll want to choose number of principal components. Though for principal components regression, we can of course use cross-validation. But the way people often choose the number of components is by looking at a plot like this. This is called a scree plot, and so people will look for some break, some bend in an elbow of this as a way to choose the number of principal components. Though there's a lot of discussion these days about how to do this in a theoretically justified way, but practically speaking,
but this would
I might
suggest
take like
maybe
8 or 9.
6, something like that.
Yeah, when as it's decaying like this, there's not really a big difference between there's not a big change in the rate as you increase the number of components. But I don't have a theoretical answer for that, but this is just an eyeballing. Here the first 7 principal components have about 40% of the variance. So we can see here, that's about somewhere around 7. Okay, so after having run PCA on this microarray data, we're going to take a look at clustering. And as in the principal components analysis, in a practical sense, what we're looking for is when we plot a dendrogram, say from a clustering and cut it somewhere that looks like a reasonable cut, what we'd like to see is that the corresponding clusters correspond to the different cancer types.
And this hierarchical clustering is very popular in the genomics community because the data is so big and wide, hard to look at. It gives them one way of looking at the data, and it became very popular.
Yes. So before we cut a dendrogram, we're just going to compare the different linkages. So we're going to make 3 plots, one for the complete linkage, one for the average linkage, and one for the single linkage. And let's see, I'll just scroll through the 3 of them and then I'll come back just so we can see the difference. So this is the complete linkage, and we note there are a few longish bars. So a bar like this is an indication that this cluster, it was far away from the next cluster it was merged with. If this is really, really long, then a cluster that it emanates from was far from the one it was finally merged to. So that's an indication that this is a good place to cut the dendrogram.
And by the way, because we know there are some cancer classes underneath this, you might expect to see a bunch of well-defined clusters at the top of this picture and then not much below.
Yes,
and that's kind of what we see in here.
Yeah, you can see here there's a group here. These are the colon cancers, and they kind of correspond to this cluster here. This group over here is mostly leukemia, and that's kind of if I cut somewhere around there. So that's what complete linkage looked like. And let's look at the other extreme is single linkage, and then I'll talk about average. So this is single linkage, and compared to complete linkage, there's really no place, if we cut anywhere around here, the results are going to be very sensitive. They're going to change a lot. So there's no natural break. And this is a common phenomenon in single linkage called chaining. And so what happens is many of these merges are just adding on a little bit to a bigger cluster. So this sort of set of, like, if you look at these values here, these are all merging single points and quite far along in the clustering process. Compared to the complete linkage, they were about halfway up the tree when those single points were merged. And average linkage, it unfortunately got a little cut in the page here, but it's sort of in between the two. There's maybe a few places, a few clusters. I mean, this range here might produce some clusters, but it's not exactly as clear as complete linkage. Okay, So now we're going to cut. So it looks like if we cut somewhere around here, there are pretty, there are some nice looking clusters that we can see by eye, and we'll color them, and then we'll take a look at the labels to see if we recovered things like this colon cancer group and this leukemia cancer. Okay, so I'm going to cut the dendrogram. We're going to cut at the level 140. Let's shrink a little bit. Let's see, these purple ones, it's rather small, but they seem to be mostly leukemia with the exception of these two, and I'm not an expert enough to know. Those might be a form of leukemia.
We can make it a bit bigger because we can see the
Yeah,
colors.
we can see.
Here.
That's a good point.
Yeah.
And these red ones, it's mostly a colon cancer, though a few breast cancers were included. And again, I'm not certain enough to know what that type of cancer is. So this isn't, perfect. This cluster over here, it has a mix, maybe a majority breast cancer, but certainly not pure. And unfortunately, we can't expect to get perfect separation into classes unless there was a really, really strong difference.
Well, also remember there were 13 different types of cancer here. So by cutting and having 4 groups, we necessarily are merging some.
That's a good point.
So what you'd like to see is, say, for example, in the green, there's merging of some cancer classes, but these cancer classes don't spread into other clusters.
Yeah. So there is a subcluster maybe here of renal, but yes, yeah, that's a good point. With only 4, we can never get all 13. And also, we only had 64 subjects. So to really distinguish the cancer types, we probably need more subjects than that, especially because we have 7,000 measurements on each. So that's an example of 2 places where unsupervised methods might be used. The remainder of the lab also does k-means clustering on this data, but as we mentioned before, hierarchical clustering is sort of more commonly applied to this kind of data set. So we're going to leave that for you to do offline.